We're going to start our discussion of internal flows with Poiseuille's equation. Now, internal flows are bounded on all sides. They're completely enclosed. Now, they often start out as nearly uniform and go through a period of development. And during this period, the shape of the velocity profile, or the velocity as a function of position, is continuously changing due to the pressure and the viscous forces acting on the fluid. Eventually, these forces become balanced, and at this point, the flow is considered fully developed. So in fully developed flow, the velocity is no longer a function of the axial distance, only distance from the wall. So radius in a pipe, or y between two plates, or something like that. For now, we're just going to focus on fully developed flow in a round pipe to demonstrate some of the behaviors. Now, however, there are similar solutions for many different types of geometries. We're also going to start by concentrating on just laminar flow, and I want to recall from our discussion on Navier-Stokes equation in Module 2 that for laminar flow in a pipe, the velocity profile is parabolic. So we have this function for the velocity profile. And we can use this result to find an even more useful equation. So Poiseuille integrated the velocity profile to get the volume flow rate for laminar flow in a pipe. This is important for two reasons. The first reason is that Poiseuille's equation provides us a relationship between pressure drop and flow rate. So if we measure the pressure drop and we know the length and the diameter of the pipe and we know the viscosity, basically the temperature, we can calculate the flow rate. So this gives us a way to measure the flow rate. And it's a very easy way to measure flow rate in laminar flows. The second reason requires a little bit of extra math to understand. If we rearrange Poiseuille's equation, we find that the dimensionless pressure drop depends on Reynolds number and dimensionless length. So now we can see that pressure drop depends on Reynolds number. We can further rearrange this equation to find the change in the energy grade line, or the head loss due to friction. Pressure drop divided by density gives us the head loss. So this is the head loss, and it represents the conversion of mechanical energy into thermal energy due to friction. If we remember from the previous module, we had this U2 minus U1 term when we derived the Bernoulli equation from the energy balance. So that term becomes the head loss. It's the energy that's converted into heat by friction. In turn, this gives us a definition for what we call the friction factor. The friction factor is a dimensionless parameter that we multiply by L over D to come up with the dimensionless head loss. Now, it may seem redundant here. We have Poiseuille's equation, so we can obviously see that the friction factor is 64 over Reynolds number from Poiseuille's equation. However, the concept of the friction factor becomes important for turbulent flows, which is going to be our next discussion. We can also convert this to the idea of hydraulic resistance. So we can say that the pressure drop is the hydraulic resistance multiplied by the volume flow rate, and we can come up with a variety of equations for the hydraulic resistance for different types of channels. And then we can use this, or at least the approach, to easily compare different geometries. So lower hydraulic resistance means that a system is more efficient. You need less pumping power to obtain the same flow rate or to move the same amount of fluid. So my question for you is, why are water pipes round? Turns out that round pipes have the smallest resistance for a given flow area. Essentially, they have the smallest surface area to volume ratio, which means that they require the least pumping power and are the most efficient. My second question is, if round pipes are the most efficient, then why are air handling ducts square or rectangular instead of round? It turns out that square ducts are much cheaper to build than round ducts, which decreases the initial capital cost of the system. Sometimes this is actually worth the increased pumping power over the life of the system. Especially with air handling systems, moving air doesn't take much energy because it has a low density and a low viscosity. So the reduction in the capital cost is actually larger than the increased pumping power required.